So we are doing IBDP equilibrium, and part 2, that is when equilibrium is disrupted. We have to apply Le-Chatelier's principle, right? Now, how do you apply this Le-Chatelier's principle, right? Now, if you see that whenever we are disrupting our equilibrium, right? When you are disrupting our equilibrium, right? To remember that the equilibrium, if you are disrupting, suppose we are trying to take this reaction, suppose we are disrupting the equilibrium, right? Suppose this we are taking, suppose we are doing this, suppose we are taking this, right? Suppose we are taking a reaction, right? N2 plus 3H2 gives you 2 ammonia, right? This. In this reaction, we have to understand that whenever we are taking a reaction, right? Whenever taking a reaction, right? Whenever we are taking a reaction, right? And we are actually doing what? This reaction, this equilibrium reaction, right? Will continue to be at equilibrium, right? This reversible reaction will continue to be at equilibrium, right? It will continue to be at equilibrium. Till then, we do not disturb, right? We do not disturb, right? Till the time it will be continue to equilibrium, be at equilibrium. Till the time we don't disturb the concentration, pressure, and the catalyst, right? And the temperature, right? We don't disturb, right? But once we disturb, right? When we disturb, what happens? The reaction will move in a particular direction, right? There are two particular directions, forward, backward, right? Is it clear? Guessing forward and backward. When we disturb this equilibrium, right? The equilibrium will move in such a direction to restore the equilibrium, right? Isn't it? And to minimize the change, right? The reversible reaction will move in that direction, which will minimize the change, right? Isn't it? Minimize the change, right? Now see, if you're seeing a reaction, reversible reaction at equilibrium, right? This will be continue to be at equilibrium, right? Till the time rate of the forward direction will be equal to rate of the backward direction. Is it clear? Right? Is it clear? This reversible reaction will continue to be at equilibrium till the time the rate of the forward direction is equal to rate of the backward direction. Is it clear? Right? Till the time the rate of the forward direction will be equal to rate of the backward direction, right? This will be continue to be at equilibrium, right? But once you are disrupting the equilibrium, right? Isn't it? Once you're disrupting the equilibrium, how? When rate of forward reaction will not be equal to rate of the backward reaction, then the equilibrium will be disturbed. Is it clear? This equilibrium reaction will continue to be at equilibrium till the time rate of the forward reaction will be equal to rate of the backward reaction. Whenever we are seeing that the rate of the forward reaction is not equal to rate of the backward reaction, right? Then we can tell that the equilibrium is disrupted. Got it? Understand this thing? The equilibrium will be disrupted, and the equilibrium will be moving in a particular direction to restore the equilibrium, right? Did you guys see? Now going to this thing, now if you see that whenever we are seeing that suppose we are seeing that we are changing the concentration, right? Isn't it? We are changing the concentration. What we are doing? Suppose you are taking this reaction, right? And we are doing what? We are suppose lifting the hood, right? Isn't it? We are lifting the hood, and we are adding nitrogen from outside, right? Anna, is it clear? We are adding nitrogen from outside, right? What we are doing? We are taking this reversible reaction, right? And at equilibrium has been reached. We lift the hood and add nitrogen from outside, right? Nitrogen from outside. Now, can you guide me that which direction the equilibrium will shift to restore the equilibrium? We have to know about Le-Chatelier's principle. Le-Chatelier's principle says what? When our equilibrium is disrupted, the equilibrium will move in that direction which minimizes the change, right? Is it clear to you? Which minimizes the change, right? Is it you? Did you guys see? Yeah. When you are taking a reversible reaction at equilibrium, it moves in that direction which minimizes the change. Is it clear? Which minimizes the change, right? Is it clear? Minimizes change. Now tell me, if you're adding nitrogen from outside, so you are deliberately increasing the concentration of this N2, isn't it? Isn't it? Can you tell me which direction the equilibrium will shift? The forward or to the what direction? Tell me.
To the right.
To the right. Very good answer. Right? Why? Because to the right, the concentration of nitrogen is used up, right? Isn't it? Nitrogen is used up. It will move to the right, right? And how does it move? How does it move? Earlier, rate of the forward direction is equal to rate of the backward direction, right? How does it quickly move to the forward direction? By increasing the speed of the forward direction. Quick, isn't it? Got it? You guys think? Equilibrium the forward direction speed quickly. Did you get this thing? Quickly increasing the rate of the forward direction, right? And see, the equilibrium is disrupted now, right? I told you what, till the time rate of the forward direction is equal to rate of the backward direction, the reaction continues to be at equilibrium. When this is disrupted, right? When this is disrupted, right? Then only the equilibrium breaks. And see, and the new equilibrium will be formed. And which direction the equilibrium position will be shifting? Tell me. Now, as the reaction moves forward direction, it moves. The rate of the forward direction increases, right? So the ammonia will be increasing, right? Ammonia will increase, right? This will increase, right? Isn't it? So now the new equilibrium position will be formed which direction? The product side or to the reactant side? Sana?
The reactant side.
The reversible reaction is moving to the forward direction quickly. What is formed more? The product is formed more now. In the equilibrium mixture, the product will be more, right? Now. So the equilibrium will shift to the product, right? Is it clear? Did you guys think? I'm just asking another question, right? Suppose you are taking this reaction N2 plus 3H2 is equal to 2 ammonia. Now you are lifting the hood, right? You are taking this closed system, right? And you are taking out ammonia as it's formed, right?
Right.
Taking out ammonia. Which direction the equilibrium will shift? Tell me.
To the right.
Now you are decreasing the concentration of ammonia, right? Isn't it? What are you taking? You are taking out ammonia from the reaction mixture. What you are doing over here, Sana? We are decreasing the concentration of ammonia, right? Intentionally, right? Isn't it? We are decreasing the concentration of ammonia, right? Isn't it? We are decreasing the concentration of ammonia, isn't it? Did you get this thing? We are intentionally decreasing the concentration of ammonia, right? Isn't it? When you are decreasing the concentration of ammonia, which direction the equilibrium will shift? In the direction where the change is minimized. What's the change? Decreasing the concentration of ammonia. The change will be minimized means what? You have to increase the concentration of ammonia. Isn't it? Now which direction the equilibrium will shift? Tell me.
It would shift to the right.
Towards the right. Because in the right, the concentration of the ammonia increases. Did you get this thing? Fine?
Yeah.
You get this thing? The concentration of ammonia increases. Did you get this thing clearly now? Fine?
Yeah.
Is it clear? So this is very crucial that when we are taking this reaction, right? Whenever we are taking this reaction, right? The reaction will move to the right, right? Now, how does it move to the right? Earlier rate of the forward reaction is equal to rate of the backward reaction, right? How does it quickly move to the right? By increasing the rate of the forward reaction speed, right? Then the backward reaction. Is it clear? Did you get this thing? It quickly moves to the it will be quickly moved to the forward direction, right? By how? By increasing the speed of the forward reaction. See, now this condition is broken. See, this condition is broken, right? So the reversible reaction is not at equilibrium. Now, could you tell me that which direction the equilibrium position will be shifting? What is equilibrium position? The proportion of the concentration of the reactant and product, right? At equilibrium, right? Is it clear? It's called as equilibrium position. Is it clear? The proportion of the reactant and product at equilibrium is called as equilibrium position. Is it clear to you?
Yeah.
Fine. Fine. So this is very important that whenever we are seeing that the equilibrium position will be shifting in which direction, Sana?
Repeat that again. Sorry, I couldn't hear you.
Which direction the equilibrium position will shift? Which direction the equilibrium shifts? Forward or the backward direction? Equilibrium shifts where? Forward direction. Right?
Forward.
Quickly to increase. So more and more amount of product will be generated now, isn't it? Isn't it? So the equilibrium position shifts where? To the forward direction or to the backward direction? To the forward direction. Is it clear to you? Is it clear? Equilibrium position will be shifting the forward direction, right? More amount of product will be generated, right? Is it clear? Any questions? Please tell me.
No questions.
Thank you so much. So this is very crucial for us to understand, right? This is very crucial, right? Now going to the next part, right? Now going to the next part. Now, if you see that whenever we are seeing that the reversible reaction, we change the concentration, we get it, right? Now doing what? Now we are trying to see that what is the changes which happens when you increase the pressure, right? It is pressure. Now remember this thing, those reactions which will be influenced by the pressure change, right? Those reactions which will be influenced by the pressure change, right? That has to be gases, right? Is it clear?
Yeah.
Which reaction will be influenced by the pressure change? Those reactions where we are having reactant and product as gases, right? Is it clear? Gas only. Did you get this in? Fine. Isn't it clear to you? You are having what? Reactant and product as gases. Is it clear? They will be gases.
Clear.
First. Second is that the total number of moles of the reactant, right? Total number of moles of the reactant should not be equal to the total number of moles of the product. Is it clear? Did you guys think? Fine. Second is what? The total number of moles of the reactant should not be equal to the total number of moles of the product. Sana, is it clear? Fine. You guys see? So this is very important that whenever we are seeing that the total number of reactant and total number of moles of the product should not be equal, and the reactant and product should be gases. Now we have to learn what? We learn that if you're seeing that, suppose we are seeing this reaction, right? Suppose same reaction I'm taking, N2 plus 3H2 gives you 2 ammonia, right? Yes, right. Now in this reaction we are seeing what? In this reaction we are seeing that if you increase the pressure, right? Now write down it. If you increase the pressure, the reaction moves to the side with less number of moles, right? Is it clear? Less number of moles. Have you wrote?
Yeah.
If you increase the pressure, which direction it shifts? It's the reaction shifts with the side with less number of moles. Clear?
Yeah.
Did you guys think? Which direction it shifts? It shift to the direction with less number of moles. Sana, is it clear?
Clear.
Now, which direction it will be moving? If you increase the pressure, forward or put it backward? The total number of moles on the reactant is how much? 4. Total number of moles in the product is 2.
Forward reaction?
Forward direction. Is it clear?
Yeah.
Is it clear? And which side the equilibrium position shifts? Tell me.
To the right.
To the right. Is it clear? And how does it quickly move to the right? By increasing the forward direction speed quickly than the backward direction. Isn't it? Clear? Did you guys see? Sana? Now, if you decrease the pressure, right? If you decrease the pressure, the reaction moves to the side with what? Side with more number of moles. Is it clear?
Clear.
Did you guys see? So this is very important for us to understand that whenever we are decreasing the pressure, it moves to the side with more number of moles. Is it clear? Fine. Right? Did you guys see? It will decrease, it will go to the side with more number of moles. Did you get this thing?
Yeah.
Fine. So this is very important that if you're seeing this reaction, right? We can easily identify that suppose we are decreasing the pressure, right? Decreasing the pressure. Which direction the equilibrium shifts to? Tell me. When you decrease the pressure?
It will shift to the left. So
to the left. How does it shift to the left? Quickly? By increasing the backward direction speed. Quickly. See, the equilibrium is destroyed, right? Rate of the forward direction is equal to rate of the backward direction at equilibrium, right? This is destroyed, right? And the equilibrium position shifts to which direction? To the reactant or to the product? Tell me.
To the reactant. To the reactant.
To the reactant. Fine. Did you get this thing clearly? Easy, right? Now we are taking temperature, right? We are taking temperature, right? When we say temperature, right? So how do we understand, right? Understand that the temperature changes. How do we understand? We do that temperature. We'll be doing what? Now write down. If you are getting a reaction like this, right? 1N2 plus 3H2. gives you 2 ammonia. You'll be getting a data over here like this, right? The delta H is equal to minus 200 minus 29 kilojoules per mole, right?
Right.
We're getting a data like this, right? Isn't it? What does this data tells you? You'll be getting a data like this, semicolon, minus 290 to 29 kilojoules per mole, right? Isn't it? We'll be getting a data like this, right? Did you get this thing? Now over here, we have to understand that whenever we are seeing this data, minus 29 kilojoules per mole, what does it tell you, Sana? It tells you that the forward direction is exothermic, right? And the backward direction is endothermic. Sana, is it clear?
There.
Did you guys see? What does it tell you? It tells you that the forward direction is exothermic, the backward direction is endothermic. This tells you, isn't it? Isn't it? It tells you the forward direction is exothermic, the backward direction is endothermic, right? Right? Any questions?
Right.
This is the thing
No
we got.
question.
Now, if we now let me write down this. If we increase the temperature, right? Any questions you got now? Immediately write this. Seeing this sign, immediately write exo, endo, right? Correct? Immediately write. If you see that whenever we are seeing that we are increasing the temperature, right? If you increase the temperature, the reaction moves to the direction with, tell me, when you increase the temperature, the reaction moves to the direction with endothermic direction, right? Isn't it? Right?
Right.
Is it clear? Can you understand this part? When you increase the temperature, the reaction moves to the direction with endothermic direction, right? Clear? Now, if you are increasing the temperature, the reaction moves in the endothermic direction, right? Isn't it? Now, can you tell me that if you're increasing the temperature to this reaction, which direction it moves? This. Tell me.
It will move to the left.
It is moved to the left, right? Isn't it? Left. Which I forgot a very important part. I'm sorry. When you change the concentration, right? The Kc does not change. Write down this, right? Right? Kc does not change, right? Is it clear? Fine.
Right.
The equilibrium position changes. We have learned, right? Equilibrium position changes, right? If you change the pressure, right? The Kc does not change, right? Fine. And the equilibrium position changes. We know this, right? Now remember that thing. Whenever you're increasing the temperature, right? When you increase the temperature, right? Fine. The Kc changes. This is the thing you have to understand. Fine. And the equilibrium position changes, right? Is it clear?
Right.
This is clear to you. So now if you increase the temperature, you said that the reaction moves to the left, right? Now, how can you quickly move to the left? Tell me. Because rate of the backward direction quickly increases, right? Than of the forward direction. Is it clear? Right? Rate of the backward direction quickly increases than of the forward direction. Isn't it? Did you get this thing?
Yeah.
Right? So this is the way it will be quickly increasing, right? Than the forward direction, right? And what happens? The equilibrium position will shift to where? Forward direction or back of the direction, backward direction? Sana?
Sorry, repeat that again.
Equilibrium position will be shifting where? Forward direction or backward direction?
Backward direction.
Yes, perfect. Now, if you see that the temperature here decreasing, right? If you decrease the temperature, the reaction moves in the. Acha, just 1 minute. Acha, let me complete this. To the exothermic direction, right? Fine. Fine. And which direction it shifts? Exothermic direction. Now, if you decrease the temperature to this reaction, which direction it shifts? Sana?
Right.
Right. Is it clear? How? Rate of the forward direction quickly increases than of backward direction, right? Yes. Isn't it? Quickly increases than the backward direction. Right, Sana? Is it clear? Fine?
Yeah.
You guys think? So it quickly increases than of the backward direction, right? And what happens? What happens? The equilibrium position shifts to the what? Which direction? Equilibrium position shifts to which direction, Sana?
It will go to the right.
Right. Perfect. Now see, now we have to learn that the Kc will be changing, right? This Kc changes, right? Is it clear? The Kc changes. Did you get this thing? The Kc changes. The Kc will change, right? Is it clear? The Kc changes. Over here, we have to understand that whenever we are seeing the Kc changes, right? How can you tell? See, if you're saying that we are decreasing the temperature, right? Right? If the temperature decreases, right, it will move to the exothermic direction. It moves to the forward direction. Okay. Now, Kc value change, right? Kc is got product to the power of stoichiometry, right? By reacting to the power of stoichiometry. Did you get this? What is Kc? Kc is product to the power of stoichiometry by reacting to the power of stoichiometry, isn't it? Isn't it? This is the thing we get. Now, if you see that whenever we are decreasing the temperature, right, the reaction moves in the exothermic direction, and in this reaction, the exothermic direction is the forward direction, right? So it moves to the forward direction, right? Isn't it clear? Moves to the forward direction. Now, my question to you is that whenever it moves to the forward direction, right, isn't it? What happens? The product increases, right? Isn't it? Isn't it? The product increases, right? So this numerator will increase, right? Isn't it? Right? And the Kc value will decrease or increase? Sana? Kc value will decrease or increase? Tell me. If the product, if the concentration of the product will be increasing because it moves to the forward direction, right? Isn't it? Moves to the forward direction. The concentration of the product will increase, right? Isn't it? So the Kc value will increase, right? Is it clear?
Clear.
Did you get this thing? Fine. Now come to the part of what? Come to the part of. Can you take a screenshot of this?
Okay. Got it.
Okay. Thank you so much. So we are getting this part that if we see that whenever we are seeing that the Kc, right, will increase, right, if the product concentration increases, right? Now we are coming to what? The change in concentration, right? Right. Sorry, the change in catalyst, right? Now, what does the catalyst do? Tell me.
Oh, it
What does the
speeds up
catalyst do?
the rate of the
Speeds up the reaction. It speeds up the rate of the reaction by providing a what? Providing an alternative pathway, right? Right. That has a transition state lower. It will speeding up the rate of the reaction by providing an alternative pathway at a lower activation energy, right? Is it clear? It will be providing an alternative pathway at a lower activation energy, right? Fine. Now, if you see that whenever we are seeing this is the forward direction, right? The forward direction, right? The forward direction activation is what we learned yesterday is this, right? Right, this forward direction activation energy, right? Now, it provides the alternative pathway. Now, it provides the alternative pathway this. So this is the activation energy, right? Is it right? The activation energy, great, isn't it? This is the activation energy. Now, if you see this reaction, right? If you see this reaction, the activation energy got lowered by what? What about this amount, right? This amount, right? Isn't it? Isn't it? Isn't it? It provided an alternative pathway at lower activation energy. So this was the earlier activation energy, this. Now it provided an alternative pathway at a lower activation energy, right? So it is this, right? Is this, right? Is this lower activation energy? Now, how much did the activation energy lowered by? This amount, right? Isn't it? This amount. Did you get this thing? This amount.
Yeah.
Right? Now, if you see the backward direction, right? If you see the backward direction, the backward direction is this, right? And what is the activation energy? Can you draw? This becomes a reactant. So reactant to the top of the hill, right? This is the activation energy to the backward reaction, right? EB. Now it lowered by what? It lowered by this amount, right? So the backward direction will be activation energy is this, right? How much did it lower by? It lowered by this amount only, right? Isn't it? So the lowering of the activation energy is equal in the forward and the backward direction, right? Isn't it? So the rate of the reaction, right? Rate of the forward reaction increases by the same percentage. Is it clear? And the backward direction, right? Rate of the backward direction also increases by the same percentage. Did you get this thing? Fine. Did you guys see? The forward reaction and the backward reaction increases by the same percentage, right? Is it clear? Right? Hence, the equilibrium position does not change. Sana, is it clear? Does not
Yes.
change. Sana, can you just quickly do one thing quickly? Yeah.
Okay.
Okay.
So what will happen to the position of the equilibrium and the value constant when the temperature is increased? It is endo.
Endo. What I'm telling you? Wait. When you were having this question, right? Write exo and endo immediately, right? It's endo,
Okay.
write exo over here, right? Is it clear? Endo, exo. Is it clear?
Okay. So okay, I see. It will shift to the
Wait. First, write down endo and exo on this arrowhead. Write down.
endo.
Right. Wait. I'm just increasing the size. Now do it.
Okay. Endo, exo, right?
Now you have to go. Don't jump from one Excel to the other, right? No. Don't jump from one. Just come to this. Cross out from left to right. Whatever wrong, right?
Okay.
Do it.
So it would favor the left, so the reactants. So not here, not this one. Okay.
Now come to this over here. Now it will move to the reactant, right?
Yeah.
Wait. When temperature is increased, which direction does the reaction goes? Endo or exo?
And this is for the.
Wait. Tell me one thing. Whenever you are increasing the temperature, right? Which direction the equilibrium shifts? Endothermic direction or exothermic direction? Did you take a screenshot?
I did.
Yeah, endothermic direction.
Let me
You
check.
taken a screenshot? Please open the screenshot.
Oh, so then I have a question then. 1 second. For here, it's for exact that the for reaction is exo and then the backward reaction.
Why? What is written over here? What is written over here?
This is the positive. It's endo.
Means that forward direction is endo. That means this. When a data like this given, right, with a semicolon, what does it mean? The forward direction is endothermic, right? Is it clear? Did you get this thing? If the data was given like this, right, the forward direction will be exo.
Right.
Isn't it?
Okay. And then if the temperature increases, it favors the endo side, right?
And in this reaction, the endothermic reaction is in the.
So shift to the products.
Yeah.
Oh, okay, I see. Okay, then the case it would
Now we have to draw the Kc. Kc is how much? Kc is equal to product to the power of stoichiometry by reactant to the power of stoichiometry, right?
Right.
Isn't it?
So if the product increases, then this increases.
Yeah.
Okay, I see.
Easy? Now it's easy for you?
Easy. Yeah.
Lovely.
That makes sense.
So this was all about what? This was now tell me this thing.
Okay.
Question number 12.
Which changes will shift the equilibrium to the right? Adding a catalyst? No. Decreasing the oxygen concentration? Yes. Increasing the volume? Yes. Because there's 2 moles here.
We'll be shifting the equilibrium to the right. Does adding a catalyst changes the equilibrium position? First tell me. No, that's the thing you have to understand. Equilibrium position is changed by concentration, changed by temperature, changed by pressure, right? Equilibrium position does not change with catalyst, right? Is it clear?
Clear. And then decreasing.
Shift the position of the equilibrium. This is wrong, right? No, this won't. Decreasing the concentration will do what? Yeah, decreasing the concentration will shift to the right. To the right. Isn't it? and increasing the volume of the concentration. Volume, this is a very tricky question, right? This is a tricky question. What does volume has with pressure? First tell me. We did
If
don't
you
we learned volume, right? We learned pressure, right? We did.
yeah.
Tell me.
So if by increasing the volume you have a decrease of pressure,
Yes. Pressure
which
decreases.
means
Which side it goes? It goes to the
the
side
one
with
with the more moles.
more number of moles, right? Isn't it?
Yeah.
Isn't it?
So 2 and 3, so go to the right with these two. So it will be C.
Do the 13.
For each of the following reactions, predict in
Here,
which direction.
here.
Oh,
14.
14.
Do
Oh,
14.
sorry.
Yeah.
Okay, how will, so this is endo, respond to the following changes. Okay. Addition of hydrogen. So that means there's an increase of hydrogen.
Wait. You didn't write over here endo exo, Sana? I told you
Okay,
whenever
so
you have got this information, immediately jump and write endo or exo like that.
okay.
Yes.
Endo exo. Sorry.
Yeah.
Okay. So then it'll go to the left, right? Because the hydrogen increased.
Addition of hydrogen goes to the left. Perfect. Now tell me.
Okay. And addition of this one, it increases, which means it'll go to the right.
Mhm.
If there's a decrease in the volume, there means there's an increase the pressure, which means it's the one with less moles. So 3, 5. So go to the left. There's a removal of S2. So decrease, which means you'll go to the right. And then there's an increase in temperature. When there's an increase in temperature, it favors the endo reaction. So it'd be the right.
Perfect. Clear now? Is it clear?
Okay.
Perfect. Now you're completely grip of this chapter.
Yeah.
So this is what this is the equilibrium portion, right? We have completed, right?